Hello everyone. Today we're adding math to our Better C compiler. Essentially, right now we only allow a number in here and nothing else, just one number. But I want to be able to do something like a plus operation, addition, like subtraction, multiplication, or, several of the operations, or even, the parenthesized expression. So essentially, how to do it? There are two parts to it. The first part is to parse this out. Our parser does not support it, of course. But the second part is to emit the actual assembly. So actually compile it, so you will be able to run the program that will calculate the whole expression. So I'll explain the first part implemented, then explain the second part implemented. So let's go. And by the way, the first thing is, let's get some tea. It's very tasty. All right, how do you implement parsing of the mathematical expression? Well, essentially, what we say is there is a rule for everything. So, for example, if we want to parse a number using a Backus-Naur-Form, we say, okay, a number is a rule. What does number consist of? Well, essentially, number consists of several digits, which is what? Which is essentially one or more digits. So plus means one or more of the previous thing, so one or more digit. Okay, cool. But, well, that's reasonable, but what if we want to allow our number to be either integer or a floating point number? Well, then we say something like, hey, it's either this or this. So digit, so several digits, or several digits, then a dot, and then also several digits. So this way you can express pretty complicated rules with just several elements, essentially just the plus, which is one or more, the multiplication, which is zero or more, the pipe, which is or, and you just declare the rule. And of course you have some, some characters. Okay, well, sure, but how does that help in parsing our mathematical expression? Well, okay, let's try to solve a simpler problem. How would you parse like an expression of 5 times 6? Well, it's number, then it's a multiplication, and then it's a number. Okay, reasonable. What if you add more, right? What if you add like a plus operation, then division? Well, essentially, all you say is you have an operation, you have a number, and then pairs of operation number, operator number. So how do we say it in BNF? Essentially, we say it like this. So we have at least one number. Well, and you say it's a math expression. It's a rule math expression. You have at least one number, and then zero or more of operator, and then a number. Well, look, a number, then operator number, operator number, operator number. Okay, great, that works. Okay, not really though. What if we want to parse something like, well, I don't know. We want to add parenthesized expressions. So, well, how do you do that? Okay, you have to think about it. This, like, how do you evaluate this expression? How do you calculate this? Well, first you calculate the thing inside of the parentheses. So you calculate the one, and then you do the regular thing. Then our rule for number, operator number, works. So the only thing we need to change is, instead of parsing this as a number, we have to treat those parentheses as a number themselves, essentially. But they're not really a number. That's why we have another rule, which is usually called atom. Well, what it states is a number or a parenthesized expression. Okay, parameterized math expression, essentially. And now, if we replace the numbers with atoms, our math expression parser, works really good. So it will parse this thing. So it will look at, okay, we have an atom, which is a math expression. It calls the math expression recursively. Then it has operator, also an atom, which is just a number. Operator, also an atom. Operator, also an atom. Amazing. So essentially, this is how you parse a mathematical expression, which is, I mean, it's very nice. But okay, let's go and just make it work. Let's go and implement it. Okay, so we have currently just parsing that will return a string of assembly, but well, not very useful. So what we have already done is we tokenize. So we break down all of our whole file into tokens. So exit is a token, for is a token, parentheses is a token, and same way here. The minus is a token. All of those are tokens. So we just need to make some rules. Here we essentially made the rules. It's just that the number is a token and the string is a token. Everything else is just a rule we define in the grammar. We just need to ensure that the tokens are arranged in the correct order. So essentially, we just need to implement this BNF. Okay, let's go. How do we parse that? Well, essentially, we say we'll have two functions: parse math, and parse atom. Let's start with parse atom. Okay, so what do? We have an array of tokens, and we consume it one by one. Essentially, we say, okay, we're currently on the first token. Then, if it is correct, we're like, okay, good, let's go next. Then we're on the second, the third, and we go along that token stream until we ensure that all the tokens follow our grammar, follow our rules. Currently, all the parser rules will directly produce assembly. It's the easiest way to get there. For now, we'll print not assembly, but we will print back to you the parsed expression, just parenthesized. Okay, so what does parse atom will take in? Well, it for sure must take in the tokens. And if we want to call the parse atom from another parse function, we also need to pass in the location, the current token we're at. So it's very easy to do that if we just create a structure parser. Let's go with that. So yeah, essentially we have just an array of tokens and a position of the current token we're parsing. So now we'll need to ensure that the first, so either the current token is a number or the current token is an opening paren. So essentially, if the current token is not a number, then we'll need to check if the current token is a paren, and then if none of those work, it's an error. By the way, you probably can't see a lot here, so let me zoom out a bit. So since we're currently the only way to get the first, so the number I check the kind, but for the paren I can literally check the first character. The only case when the first character is open paren is if it's the paren. There are no other ways to get this condition. And yeah, we need to handle as well the error case. Well, I will literally just return an incorrect string, the null string. So in the case of of the successful parsing of a number, we essentially, so currently I just want to debug that our parsing works, so I will just return the string of the number. And of course we need to go forward, so we need to increase the position. And sort of the same goes for the second rule. We just need to ensure, we need to recursively call the math expression and ensure that after we call it, we get the closing paren. We just need to declare the parse math function beforehand. And of course, we need to check for errors that parse math will return. So we also can get the invalid null string, and this is an error state. Now, of course, if we don't find the closing paren, we also need to report an error. And of course, after successful parsing of the paren, we also need to increase the position as well. And after that, to debug our parsing, I can just literally return the result of the math parse function. I don't think for now I will not wrap into additional, or I mean I can wrap into additional parentheses, but for now it's okay. Okay, now we need to implement the parse math. So let's again remember the rule for the parse math. We parse one atom, then we parse an operator, then we parse pairs of operator and atom. So we'll just make a simple loop for this thing, and here we'll check just a single case. So we parsed a single atom, we saved it into the result. Now let's make a loop for the pairs. So yeah, if we parsed an operator, if we didn't parse an operator successfully, it probably means that we need to stop. There is no the math does not continue. So we parsed some number of atoms and operator number atom pairs, and if we don't have another operator, it means that here is the stop. So, but if we parse some atom and operator atom pairs, then we get an operator and no atom, it means that it's an abrupt stop. So what does it mean to do 5 plus 6 plus? It's an invalid grammar. It's an invalid sentence. So we need to say it's hard stop, hard error. We expect it to have an atom here. That's why we return the null string. To debug this thing, I need to essentially append the strings. So wrap the start and then append the operator and the next. So let me show. It's probably better to call it collector. So yeah, essentially we need to add append to the string first paren, then collector, then operator, next, and again paren. So we wrap recursively essentially. And of course, to append the operator, we need to capture it as well. Capture its string. Or char. Right now all the operators are single characters, so let's use char. And when we capture the operator, we also append it, and after that we append the next and the closing paren. Okay, well, now we can just return our collector, and let's try to parse some expression and print what it parses out and reconstructs. And of course we need to construct the parser when we start the parsing. So let's not keep the tokens in a separate place. Let's keep it in the parser as we put the tokens array into the parser structure. Okay, so we called the parsing of the math, and let's print what we get out of it. Now let's update our example file, or maybe create a new one. Well, yeah, let's erase whatever we had here. And first parse a simple simple single number. Well, it should work. We will expect it to work. And of course, we need to fix the errors. Oh, it's not string append, it's string add. Okay, well, let's keep the operator as a string and not as a character. And I think I know the other error. So this is fine. We can keep the keep it as a string. That's absolutely no problemo. But I know the other error would be is that I think everything should be fine actually. Yeah, it compiles. Great. Now let's run our compiler. So example BC, and we create an executable of example.out. Okay, great. Well, the result is nothing, which is not correct. Oh, of course. So I return the string of the next token. So while I parsed the number token, assured it was correct, I'm returning the string of the next token, which is of course incorrect. I need to save the string first and then append the position. Okay, let's try to run it. Okay, hey, we successfully parsed the 4. Let's make some... It's not all that interesting. We already did that before. Let's make something more interesting. Let's have a more complicated expression with with not just one number. But for now, no parentheses. Okay, so 4 times 5 divided by 3 plus 5. It definitely parsed it out. It parsed it quite correctly. Currently, the order of operations will be set using parentheses. We expect the user, the programmer, to set that. The order of operations, I will fix that in a later episode. But for now, let's just make this work, where we set the order of operations manually. This is hard enough. Okay, so let's try to parse something with parentheses. Let's make it a little more complicated, a little, more fun. Let's have less 5s and more 7s, maybe 6s. Okay, so 4. Okay, let's start with the end. Minus 6. It is at the end. Then times 3. Okay, great. Then we have... okay, times 3 is this. Then times 4, which is reasonable. Then we'll have plus 5, which is also reasonable. Then minus 7 and division. Okay, it parses everything correctly. The order doesn't matter right now. So the parentheses are parsed fine. The numbers and operators are parsed just fine. So, well, what if we do something like we skip a number? What will happen? Let's see. Well, segmentation fault. Not really the greatest way to indicate an error, but definitely is a way, right? So let's debug it. I think it should at least print an error of some sort. Actually, the easier way to debug this would be to compile with sanitizers. It will show good amount of info. If the sanitizers will not help, then I'll go to the GDB. Okay, so we got it where exactly? We got it at parse atom 120. Let's see The issue here is that our parser expects there to be an atom after the minus sign, the operator. But since there's nothing, this stream of tokens ended. And we have to check that the position is correct, that the position is less than length of the array of the tokens. So we have to check that the position is correct for essentially all of those rules, all the conditions. So let's do it. But also, one thing is, since we have to check the position for all of those cases where we use the position, well, you can see some patterns. You can see that you check the number, you check that the current token is a number, then you return the token, and of course you increase the position. Here you also check that essentially the string is a parent, then you increase the position and also return the token. Well, here we don't use the token, but it's okay. Here you also could return the token, but essentially every time you check the token, it's either you check a kind of a token or a string of a token, and then you increase the position. And you also need to check that the position is in bounds before you do the check. So let's have two functions, expect kind and expect string. Essentially, well, the more basic implementation of parsers use peek and consume, but so essentially this is the whole code for consume, and this is the whole code for peek. We can write it out ourselves. Those are not very useful functions, at least in this context. But the expect functions, they offer much more useful and general approach here. So let's implement them for our parser. They will return a pointer to a token. Since a token is a beefy structure, let's return a pointer, and this way we can also have an error reporting, like if we run out of tokens, we will return the null, right? Or like whatever. So it's a nice way to also have errors. So let's just copy the code. Essentially this is almost the whole code, which is not a lot, but from experience, I can tell you that this is usually useful abstraction for the parser. And you can see that we repeat it a lot of times. If you were to continue implementing those things, you would have seen those structures pop up much, much more. So, but I just can see from experience that this will happen, and factor it out. But don't factor things out, don't abstract too early. Here I've seen at least 3 cases, at least 3 or even more, 4 cases. And yeah, so don't abstract too often. But let's go implement this. So if we got the correct, and also we need to pass in the kind, of course, otherwise what are we expecting essentially? So if the kind of the token is correct, we get the token, then increase the position and return the pointer to the token. Otherwise, we just return the null, essentially. This is our way to say, hey, we ran out of tokens. I could also just have a static, static token and refer to that. But I don't know. I don't think we want that. And also, let's not forget that we need to check that the position is in bounds, so that we are checking the that we can even dereference, that we can even access that token from the token array. So essentially, we assume that the current position is less than the length of the token array. If it's more than we ran out of tokens, return null. If we didn't get the correct tokens, if we didn't get the correct token kind, we also return null. So null essentially is our error value. And let's also add the expect string. We'll also check for the length, that we didn't run out of tokens, and then we just check that the string is equals to what we're trying to compare it with. And let's maybe compress it a bit. And since we compressed this expression, we can also directly return, which is pretty cool. Okay, now we just need to use those two functions to parse the things. And now it becomes very, very easy to make new rules. It's super, super simple to translate our BNF notation into the actual code. So essentially, we just declare a token and we just assign to it. We assign to it and check that it's not null, of course. Then we got our string. Alright, so we just can say talk.stir. Very, very simple. Don't you find it? And here you also do sort of the same thing, just instead of kind we use stir. And it's fine that here we compare a char, and then in the stir we will compare the whole string. It's not a problem right now. If we will find later that this can be optimized and it will make our parser much faster, and we need a faster parser, then I can make a separate function expect char. But for now, expect stir will do its job just fine. And here we do the same logic, same old thing. We just need to check that we have a closing pattern. And we probably don't even need to assign it to any tokens, since we don't really care about, since we already know what's going to be the string and what's going to be the token kind. There's no mysteries here, so we don't even need to assign it to anything. And of course here we check that if we don't have the opening pattern, then we don't even go into this branch. But here, if we have the null, which means that we didn't find it, we return an error. Okay, look, it compressed very, very nicely. It compressed very, very nicely. Okay, let's do the same for the math. And we want to capture the token, so let's save it. Let's assign the token. We could probably just do that, right? But I like explicit. Explicit is better than implicit. It's just harder to make an error when you make those things explicit. Okay, we have a warning, implicit declaration. Oh, it's probably compare. Yeah, it's string compare. Let's probably separate this into two parts. I don't like how bulky it is. It takes too many lines. Now we have even less lines than previously. So instead here we just do the string compare. If it's not 0, so if they didn't match, we return null. That's pretty good. That's pretty good. I like that. Pretty tidy functions. Very, very terse. I like it. Okay, I would expect this to compile finally. Hopefully. Yeah, and it does. Let's run it. Oh, well, of course we leak a lot of memory. It doesn't really matter. And okay, great. So let me recompile without sanitizer. So we got the result of an error state, essentially. We returned the null string, and it prints 0 characters, which is reasonable. But essentially we detected the error. We just didn't print any message that we got an error, and it's reasonable to print a message that we got an error like immediately when we got the error. We have the most amount of information. So for example, like here, we can say that the parent didn't close. So essentially we just say, hey, this was not closed. Okay, at what other point we fail? Yeah. That's okay. So this is not the source of an error already. So what we'll get right now, when we recompile, we should get a print error. So expected number or opening pattern. It's not really clear where it comes from, but currently, if you look into the into the example, it's kind of obvious that we didn't complete the last part. When we will have larger files and more code, we will make a more specific error reporting that will, show the line and show where exactly it was aired out. But for now, it's okay. We just report an error, and that's already very good. Okay. So essentially, we parsed everything. Let's just stress test it one bit more. So, okay, let's complete this back, but remove something from here, for example. I would expect to also have the same error. Yeah, we also have the same error. Okay, what if I actually don't close? Let's try to open but not close. Okay, great. So essentially the errors are working and the correct expressions are parsed successfully. That's great. So we did the first part, which is parsing the expression. Now the second and the more interesting part is how to essentially produce assembly that will calculate this expression. But for now, I will like a tea break. So cheers. For now, it also would be nice to parse the exit that we had previously. So previously, our syntax was something like exit, and then at the end we essentially, oh my bad. So we had the syntax of exit, and we wrapped the whole expression to this call. So let's ensure this syntax as well, so we don't have any whatever worked before will work now. So no, we will have no regressions. Right. Well, essentially, it's all the same. We just expect a string and then expect those two things. So I can copy this code essentially pretty much directly. So hey, maybe I should factor out the null string since I use it so often. Let's just factor it out, shall we? Okay, now let's replace all the occurrences. Yeah, look, you know what? I think I can do the multiple cursors thing. Neovim, what the hell is happening? Why are you not working? The opening paren, we just return string null. And also, we expect to have the exit. And if we don't get the exit token, we'll also say, hey, something's really wrong. Try again, do better. Okay. So we parse math, we ensure that the math is correct. Well, actually, yes. Actually, I would expect to report an error there. So yeah, of course, we just expect the exit to be the first thing, and then we expect to find the opening paren. I mean, sure, we can print the math again. Let's just check that the thing also works. Okay. Oh yeah, so also we use the p as a pointer to the parser. Let's run it. Yeah, so it worked. It worked. No questions. Very good, very good. And if we delete the exit, we will get an error that we expected an exit. Yep. Pretty good, pretty good. So, but now, how do you compile this into assembly? So, the idea is, well, how do you do things like multiplication, subtraction, addition, division, or even modulo in assembly? Okay, so addition and subtraction are very easy. They're just one instruction. So well, you have registers which are just essentially integer variables. So you can do something like, say, rax equals to, I don't know, 64, 69, whatever. Okay, and we can also say, hey, you can set rbx equal to, I don't know, 5, and then you can do something like subtract, from rax you subtract rbx, or you can add them, and the result will go into rax, into the first register, listed here. Okay, that's good. They're just one instruction, very easy. But what about multiplication? So multiplication takes a register and multiplies that register by rax and saves it into rax and rdx. So if you multiply two registers which are at their maximum values, their result will take essentially the width of two registers. That's why the result is split into rax and rdx. So rdx will contain higher bits and rax will contain lower bits. But if we multiply small numbers, essentially the whole result is stored in the rax. So you just multiply rax by rbx and you will have the result in rax. That's pretty good. What about division? Well, division also divides the register by rax and saves it calculates the division and modulo at the same time. So you will get the result of the modulo in rdx, and in rax you will get the result of the division. Okay, so nice. We now know how to do those 5 operations, but that's just like essentially one time. We do this operation one time. But what if we have like a complicated expression we need to calculate? So like, I don't know. So for example, 5 minus 4 times 6 divided by 2. So okay, for sure, for the subtraction, we can put 5 in rax, we can put 4 in rbx, we can do the subtraction. So the result will go into rax. But then we need to do the division. And division requires rax. It will override the result in the rax. So we need to store the results of the previous operations. And what if our expression is more complicated? So we have more parentheses. Then we need to save even more results, and it becomes a headache very quickly, because either you need to shuffle the registers, you need to save the results, and you need to choose which registers to use. It's not very easy to implement. Well, in the end, what actually compilers do, like optimizing compilers do, like Clang, like GCC, MCVC, they all allocate registers, shuffle the memories, so like nothing overrides anything else. But, well, right now we don't have even the basic implementation. You cannot optimize non-existent implementation. It is a stupidity trying to optimize non-existent implementation. First, you have to have a implementation, the stupidest. But then when you have one, you can already have a more, faster thing. So when our compiler gets more powerful, then we see that, damn, this mathematical function runs very, very slowly. Then we look at how we can improve this algorithm. So what I'm proposing is a very, very simple solution that will work regardless of complexity of the expression. So we use stack, which is essentially just big array of memory. So you can do something like, you can push into the stack. So you can do things like push 54, like you can also push the register. For example, you can push rax, and it will literally save into the stack. The stack of, for example, dishes. Stack of dishes. You put something on the top, and you can pop something off the top as well. Okay, so the idea is you presume that for each operation you have the operands in the top of the stack. So 2 operands in the top of the stack. You pop them both. So, for example, if you want to do a subtraction, you do pop rbx, then you do pop rax. So you do the subtraction, and then you push the result. And now you don't care what the next operation will do with the rax, since you saved it on a stack. You took two numbers, essentially, you did something with them, and you put it back. And with this method, it's very, very easy to have any complexity of operations. So essentially, you just pop something, do the operation, and push it. So we can, for example, see what will happen with this operation. Well, the stupidest thing, but the fact is, it will work. So you push 5, you push 4, or you push 5, 4, then you pop, you do subtraction, you push. Well, then you also need to have here you'll have to have the 6 and the 2 pushed separately. You do division, and then you need to multiply. So essentially, you had 2 numbers on a stack. You popped 2, calculated, like put it back. Then you pushed the other 2, calculated, put it back, and then you have 2 operands on a stack. You pop rbx, you pop rax, and then you can calculate the multiplication very, very easily. And then you push the result. And then all you need to do to get the RDI is pop into RDI. And you got, the calculation is done, and it will be returned by a syscall. The program will exit with this exit code. That's pretty cool. So, okay, well, let me show you an example where something will be pushed before. So, for example, if I do something like 6, plus this whole expression, then the plus have to be essentially, the 6 have to be essentially pushed here. So you push 6, like 5, 4, then you do all the operations, and in the end, you also do the plus, the addition. So you pop rbx, pop mul, and then you do add, rax rbx. And it just works. So how to decide when to push? Essentially, well, you just do recursive. So if you parenthesize everything, you can see that here you got the first argument is 6, and then the next argument is an expression. So you push 6 and then go to the expression. Here you have one expression and the other expression. Well, you recursively go there, and of course after that you put the multiplication. Okay, here you have the subtraction. You put 5, push 5, push 4, then do the subtraction. So then the recursive call also goes here, 6 to division, and now we exit from the recursive call of those 2, we do the multiplication, and now we exit from the recursive call here, we do the addition. So like the order is just a recursion. When you have a number, you just push it. When you have a more complicated expression, you just recursively go to it. So let's just implement it. And we'll see how it works. It works. It's magic. It's really kind of magical. Okay, so let's implement it. Well, essentially what you need to do is do a switch case here on the operation. Well, since we know that all operands are characters, we can just take the first character and go with it. Single characters. All the operations are single characters. So since we know that all the operations are single characters, we can just grab the first character and go with it. Okay, so first, as we discussed, we need to push the number if we find one. So let's start with the simplest thing. Let's start with pushing a number. All you need to use is string add. This is the whole implementation of pushing a number. That's very easy. Grouping, it doesn't require any additional code. It just changes the order of operations. So of course, before the operation, as we discussed, we need to we need to pop the arguments. So, pop rbx. Let's add it to the collector. Now we do the operation. What is assembly for doing the add? Okay, pretty simple. And of course we need to push the result. Okay, for minus the code is almost the same. Multiplication, it's a little different. We do mul. Yeah, let's do the division and modulo. They essentially have the same code, which is div. You push rex when it's division, and you push rdx when it's modulo. Oh yeah, of course we still need to add it to the collector. I feel like it would be nice to separate the instructions. So maybe let's add the new line here, additional new line. Of course, we generated the assembly. Amazing. We need to incorporate it in what we already generate, in what we are already generating. Oh yeah, of course we need to break as well. Maybe we should handle the default case though. We just report an error there and return. Well, I still print it, but the debug print is no longer needed. And of course, I need to not move, but pop RDI. Yeah. 6 errors. That's a lot of errors. I guess I added the extra parentheses. It generated assembly. Let's look at it. So first, let's look at the example we got. So it's kind of it's a big example, it's not a small one. But let's look at the assembly now and compare. Okay, so we start with a 4. Oh, yeah, it's kind of the pushes. Yeah, it's okay. So we start with a 4, then why we do the popping? Isn't that what? That's weird. Look, let's turn our parsing code into recursive code, actually. So the same way I explained the thing, because currently it is a loop, right? It's a loop, but I would like this to be essentially a recursive definition. Yeah, a recursive call. So that we generated everything before. Yeah. Before we need to do the operation. By the way, I never push the next. The next goes to trash. But then, and oh, by the way, I think that it's reasonable to add the new line. Let's turn it into a recursive call. So we also should return this turn null if we got an unexpected. Okay, well, let's see. Let's recompile and try to run it. Oh. And also, by the way, I think it's not unreasonable to do something like got this. That's one thing, but why am I seeing pushes? Oh, it's the FOSM error. Right, processed push. Oh, okay, fair enough. So you add push, and then after you pushed the actual number, you add the new line. So the recursive call will generate everything from the inside, from the innermost expression to the outermost, preserving the flow. Let's see again. Now, using the recursive method, what we do first? First, we push 4, then 5, 3, 7. Okay. Then, what do we do? Okay, actually, let's not break those things apart. So, the first, okay, we push 4, 5, 3. Then we pop 2, subtract them. Okay, sure. The order of operations right now is not implemented. So, we first do this, whatever. Then we... Okay, well, the push of 5 here is actually incorrect. Or wait, no, it's the next 5. Okay, look. Let's have unique numbers. 4. No, 4 was already 2. 2, let's go with 2. Yeah. Okay, here we push the 2. Okay, great. So here we do the division with the 5. Okay, we calculated this. Then we push the 2. And we do the addition. Okay, great. Now we push 3 and 6. And we do the subtraction. And then we can do the multiplication. Well, actually 2 multiplications. This and this, and then this. Okay, great. And then we pop RDI. Alright, well, first of all, let's make sure that the order is sensible, at least somewhat. So I'll give the explicit order to all of those operations. Okay, great. Let's rerun it again. So now the order is very explicit, and we get the 5-3 division first. Then we do the subtraction with the 7. Then, you know, the addition with the 2, which is, yeah, all very correct. The only thing left, I think, is to put this expression into the best calculator ever, Python. You know, you cannot find a better calculator. It's the supreme calculator. Okay, it's 40. Well, we need to do this kind of division. Okay, 48. 48. All right. Now we can run our program we compiled just here. So let's see. Example.out. We run it. We look at the exit code. Okay. The moment of the suspense. 48! We made an actually working calculator. I mean, unfortunately though, it's limited by, size 255. So if we do something, with a bigger number, so for example, 45 here, so, and maybe, I don't know, maybe let's go with 65. And that will definitely overflow. But we can still check the correctness, at least partially. So, well, let's go. What did I do here? It's 65. Okay, 780. Now, if we recompile our program and rerun it, we get something not really correct. But why is that? Why is that? Well, because we need to just modulo. The return code in Linux is essentially just lower byte. So 255 is the maximum. So we just do the modulo 256. That's kind of it. And we get it. We get the same exact result. The last bit is absolutely correct. When we will be able to print the thing, when we will have a print function, we will see the whole 780. But for now, we enjoy the limited calculator, the calculator that will return the result maximum of 255, but has the actual, precision of 2 to the 64. So the precision is really good, but the output precision isn't very good. All right, that is very, very nice. Essentially, we added the mathematics to our compiler. It now can be a simple calculator. It can literally produce such a program. And the next step is going to be to fix the order of operations, because, well, this order of operations is quite incorrect. So it essentially does the recursion, and like it's not correct. And also the other next step is to print the result. Printing is, I mean, it's essential to get the whole 64 bits of resolution, and not just not just the 8 that return code allows us. So thanks for watching. If you enjoyed this, like and subscribe. You can also watch the previous episodes when we implemented the first compiler or the tokenizer. And we'll see you soon.